Hi everyone. Today we have Jonathan as our speaker. He's currently working in the foundational cryptography group at IBM Research Zurich. Today he's going to talk about his work, space-efficient proof systems from different cryptographic assumptions. Let's welcome him.
Thanks a lot. Actually, I had quite a bit of trouble coming up with the topic for today's talk. Because originally I thought I would talk about this recent work that I had with Alessandro and Yunsong and Michele called Gemini on space-efficient proof systems. And then I looked at the seminar website and I saw that my co-author Yunsong had actually already presented that not so long ago. And you'd also had a talk by Pratik on time and space-efficient arguments from groups of unknown order. So I thought, okay, I can give a different kind of talk on zero-knowledge arguments in like a very general algebraic setting, from all kinds of different assumptions. This work on sum-check arguments. But elsewhere on the seminar website, I saw that Abiram had already given a talk which generalized that one, algebraic reductions of knowledge. So I thought, okay, maybe I can give a talk about something else, like this work on like linear time zero-knowledge IOPs that I've had recently that was presented at Eurocrypt. And then I saw that at some point in the future, you're going to have to talk by my other co-author, Siki. So I wasn't sure what to do. And I came to the conclusion that the only way to escape this was to talk about all three different works at the same time. So I'm going to try and give a fun speculative talk where I try and highlight connections between these different works. Okay, so broadly, the topic is succinct arguments for NP. And in this setting, we've got a prover and a verifier. And they share some instance of an NP problem, like a circuit over a finite field. And the prover's got a witness, which when you feed the witness values as inputs to the circuit, gives the desired output for the circuit. And the goal of this protocol is for the prover to convince the verifier that the circuit is satisfiable using their witness. So they exchange lots of information, they communicate, and at the end of the protocol, if the verifier was convinced, then they'll accept the proof, and if they weren't convinced, then they'll reject it. So all quite standard, and we've got some security properties. Completeness, so if the circuit's satisfiable, the verifier should basically always accept. And soundness, so that if the circuit's unsatisfiable, then the verifier should basically always reject. The other property we care about is succinctness. For succinct arguments, we want the communication costs in this protocol to be a lot less than the size of the witness. So if the circuit size is n gates, then we might imagine like polylogarithmic in n. So in fact, the desirable performance parameters that we have today from different succinct arguments for NP problems are polylogarithmic proof size and verification time. Or maybe even better, there are even succinct arguments with constant proof size and verification time, and a close to linear or even linear time prover algorithm. Now, the title of this talk is Space Efficient. It's about space efficient arguments, and we'll be focusing on the memory costs as well as the time costs for the prover, and seeing how to get memory efficient provers. And mostly I'm going to ignore the verifier costs for today. As it turns out, memory is actually a really big issue in scaling succinct arguments. I've got this line here on the slide with different instance sizes n. I wonder, does anyone want to have a guess at what the biggest instance size you can run on a single computer with like a state-of-the-art succinct argument for like just a typical zero-knowledge proof system or something? Would anybody like to have a guess?
2 to the 10.
Okay.
30.
Any higher, lower?
2 to the 30.
What's the question? Sorry, what's n?
N is like the number of gates in the circuit.
You mean the largest that has been run? 2 to the 40.
Okay. So I'm just gonna add on some other points onto this graph, just like for scale. So 2 to the 14 is like the number of constraints if you want to prove that a hash function was computed correctly. We've got 2 to the 37, which is like the number of stars in the Milky Way. Does anyone want to update their guess?
2 to the 0.
2 to the 0. Oh, okay. So the correct answer on a single machine, the typical limit, if you run most state-of-the-art proof systems just in a naive way without modification, is about 2 to the 25. And they don't scale beyond that because the computers usually run out of RAM and just can't execute the proof algorithms. So just to complete this diagram, like the biggest known deployment of zero-knowledge proof systems and succinct arguments is by Filecoin, and they actually handle about 600 trillion constraints daily. So this is the top end of the diagram. So clearly we have some way to go in terms of scaling. Filecoin does actually handle this, but using lots and lots and lots of different smaller proofs, not all in one go. So we have this fun zone here above 2 to the 25, where we need to think really carefully about how the proof algorithms use memory in order to even run the proof systems without them crashing. Now, the way we can solve memory problems is, well, firstly, by just using more computers, more memory, more computers. And this was done in the past. People were able to get an instance size of like 2 to the 31 using about 20 machines. Another solution, which you've already heard Yonsong talk about, this is what we did in this Gemini work, which was to use streaming proof algorithms, which didn't use that much memory. And there, for example, I think the largest instance that we ran was 2 to the 37. And then another solution is to use these recursive proof composition techniques where you do proofs of proofs. So you can do a proof that you've seen another proof that you've seen another proof, and eventually prove these really large statements that way. Now, the first approach here, just using more machines, this is really expensive just to rent more machines, and it's not really accessible to everybody. And then on the other hand, this last option, composition with proofs of proofs of proofs, is really complex. So it involves a non-black box use of crypto, proving things, say, about like hash functions, which may also be modeled as random oracles, and maybe using tailor-made hash functions with efficient proofs, just to make all of this scale and work. So this involves some quite complicated theoretical and engineering effort. And maybe the simple option, well, maybe the compromise in the middle, which is not so difficult and has decent proofs in theory, decent results in practice, is to use these streaming provers. And that's going to be the focus of my talk today. Constructing succinct arguments with streaming provers. The motivation for a streaming prover is that we've got this memory hierarchy in computing devices with sort of big, slow, long-term memory at the bottom of this pyramid and like small, fast, short-term memory at the top. And if we just look at RAM and hard drives, like on our computers, if the witness in instance is stored in a hard drive, then most proof algorithms would just copy the witness in instance into RAM and then try and run the proof algorithm and crash for these really large instances. Another way to try and make things scale would be just to run the entire proof algorithm on a very large slow memory device, but this would be horrendously slow. So the idea behind using these streaming provers is that you can have the witness and instance live, say, in a big slow memory location like a hard drive, and just have the prover and their working memory just run entirely in RAM. And to make the most efficient possible use of this slow memory, we just have the prover say next whenever they want another piece of their input, and just keep requesting subsequent elements. We let the prover make just read-only access to all of their inputs in sequential order, and we can allow multiple passes over the prover's inputs. If the prover's got inputs of length n, say like the number of gates in the circuit, then we can allow, say, a logarithmic amount of memory and a logarithmic number of passes over the prover's inputs in this streaming model. So this isn't a new model. This has been around since about 2011, at least, where it was used to come up with like streaming implementations of various interactive proofs like the GKR protocol. So now I'm going to show you what we've actually got so far in terms of proof systems with streaming provers. So there are 2 rows in this table, and the first row is typical provers, the second row is streaming provers, because all of the streaming implementations of provers, well, most of these for succinct arguments that we've got so far, they all have like a counterpart proof system without a streaming prover, just like a typical prover, which uses a lot of memory. And then these streaming prover algorithms have been obtained by modifying these proof systems or running them in a different way so that they don't use as much memory. So we've got streaming proof systems based on the discrete logarithm assumption, groups of unknown order like RSA groups, and different types of pairing assumptions. And let's say the typical provers run in a linear amount of time and also memory. And all the streaming provers in these constructions run in quasi-linear time with a logarithmic amount of memory. Unfortunately, in this picture, we don't have any quantum resistant proof systems with streaming provers. And this is something we really ought to be thinking about. Now, the NIST post-quantum competition is finished. We've got signature schemes now. We've got key exchange algorithms. We should start thinking about more advanced primitives. And there are lattice-based succinct arguments with typical prover algorithms, and also other constructions of succinct arguments based on properties of error-correcting codes and hash functions with post-quantum security. But we don't have anything in the way of streaming provers for these types of constructions of succinct arguments yet. So I'm going to explain at least how I think about this and how we might go about constructing these types of things and what the problems with them are, like what kind of limits they have. Instead of focusing on general arguments for arithmetic circuits, we're just going to focus on scalar products. So we're going to think about a simple instance where we've got 2 commitments, A and B, and a target message value. And the prover's witness is 2 vectors, like a vector A, which goes inside the commitment capital A, and a vector B, which goes inside the commitment capital B. And then the scalar product of 2 is equal to this target value. So we're just going to focus on that. And this is okay to do because there are reductions from circuit satisfiability to these scalar product protocols. And this works with an efficient streaming prover, which doesn't use memory much, as long as the commitments themselves are computable using streaming algorithms. So the agenda for this talk is going to be, firstly, a space efficient protocol for just scalar products without any commitments. Then the next part is going to be to add in some discrete logarithm-based commitments, A and B, into this protocol. And then finally, we're going to consider how far this protocol might generalize to other types of assumptions to give us other types of memory-efficient succinct arguments. So that's the plan for the talk. Are there any questions or unclear things about the model or things I've talked about so far?
We're good.
All good? Okay, great. So first, let's talk about a space-efficient scalar product protocol. So this is where I bring in some details from that work on sum-check arguments eventually. But I'll start with the sum-check protocol from 1992. And this is going to be the basis for a space-efficient way of checking scalar products. In this protocol, the instance is a polynomial over a finite field, and we've got a target value u. And the aim of this protocol is for the prover to convince the verifier that this polynomial sums up to give the target value over a particular evaluation domain. And this is an easy language. It's actually a P language and not an NP language. So there's no witness at all actually in this protocol. We'll be reintroducing that later. In this protocol, the prover computes some polynomials by doing some partial sums. So they compute this polynomial Q1 by evaluating P and summing it up over all inputs except the first one, and then sending this polynomial Q1, which has one variable, to the verifier. And the verifier can perform some checks on this, send like a random challenge value back to the prover, and then the sum check protocol works like a reduction. So after these two moves in the protocol, the sum check basically reduces the task of checking this sum for the polynomial P, which has L variables, to checking the same kind of thing over this polynomial P prime, which has L-1 variables because X1 has been evaluated at this random challenge R1. So we've got a new instance with one variable less, a new target value that we want to sum to, and a smaller evaluation domain to sum over. And the protocol proceeds just by running more reductions until all the variables in the polynomial are gone. And the final instance is just checking that these two values are equal to one another. So one of the values, PL, is the original polynomial evaluated as a random point. And then we have this last target value. So finally, the verifier can just check that a random evaluation of the polynomial is equal to this one point, instead of doing 2 to the L evaluations. So don't worry too much about like the form of the messages. Like I flashed up this polynomial Q1 in front of everybody very quickly. It doesn't really matter too much about like the actual form of Q1 for now. What's most important is just to notice that we're reducing from this polynomial P to this new instance with the polynomial P prime, where we evaluate in one variable. So we evaluate in like one variable at a time. That's the most important thing to remember. Okay, now this protocol is pretty efficient. The prover sends a degree P polynomial in one variable every round. And this gives us a total proof size of L times the degree of P, because we had L variables, so like L reductions in total. And the soundness guarantee comes from bounding the number of roots of like a polynomial of degree P. So if you start off with an instance which isn't in the language, the chance that you can flip and reduce to something that is in the language is the degree of P over the number of points in the finite field. And this is because polynomials of degree P only have degree P roots at most. Okay, next, we're going to turn this into a scalar product protocol by choosing an appropriate polynomial P.
So the proof size is in the field element? Like...
Yeah, exactly, yeah, that's right. Yeah, so so Q1 is a degree P polynomial. And you can send that by sending the coefficients, so that would be degree P elements in the field, yeah.
Thanks.
Okay, if we want to use this as a scalar product protocol, we need to pick a suitable polynomial P that means something in terms of scalar products. To pick this polynomial, I'm going to define this other polynomial P sub A, and this is like a multilinear polynomial where every single entry of a vector A for the scalar product is assigned to its own monomial in this multilinear polynomial. So you can take the index of the vector, you can take the index of an entry AI in the vector A and decompose it into binary. And you can use these bits as like the powers to produce this monomial that this entry of A is multiplied by. Oh, I think there's a question in the chat. How could we make the prover efficient with sum check for CSAT when the prover has to sum over an exponential domain at almost each round? Okay, so it's exponential in L. So actually this, you see this polynomial that we're going to pick here has log n variables. So L is equal to log n. And then the total size of the evaluation domain is actually capital N. So there's not going to be an issue because, well, it is exponential, but we're going to choose L to be logarithmic. So that's going to be fine. I see this is for generic CSAT in general. I'm only talking about a scalar product protocol today, but yeah, there are reductions from general circuit satisfiability just to doing these scalar product protocols with this parameter setting. So this is like the main subroutine, and it does give you eventually like an efficient succinct argument for circuit satisfiability. Yeah. Okay, to actually pick our polynomial p, we're going to make use of this claim, this claim that I'm going to prove on the next slide, or at least explain that if we have this polynomial p sub a for a vector a, and also p sub b for the vector b, then when we sum up over this domain, we get like a multiple of the scalar product of these two vectors. And using this fact, we can just check a scalar product by running a sum check protocol with a polynomial p, which is pa times pb, and like a target value, which is n times the scalar product value that we wanted to check. So coming up next, I'm going to explain why this claim is true. And then we're going to talk about how this scalar product protocol, how this like sum check protocol can be made space efficient, and why the prover doesn't have to use that much memory. Oh, right, yeah. So since we've chosen the number of variables to be logarithmic in n, and the degree of the polynomial is constant because like pa and pb are both multilinear polynomials, we end up with a logarithmic communication protocol in the end. Okay, so the fact that this protocol works makes use of this claim about summing polynomial evaluations to this scalar product value. The reason that this works is that inside the sum, summing over plus and minus 1 just cancels out and destroys any monomials which have odd degree in any variable, like this one, x1, x2 squared, x3 squared. And so the only terms that survive the sum are monomials where all the powers in the monomial are even, so either 0 or 2 in this case. And then since PA and PB were both multilinear polynomials, the only contributions we get surviving in the sum are from when the ith term, like the ith entry of A and its monomial, get multiplied by the ith entry of B and its monomial. So A1 times B1, A2 times B2, A3 times B3 are kind of the only terms that survive. And that's how we end up with this scalar product relation up to this extra factor of n. Okay, so that was like all the hard work, understanding how to set parameters for the sum check protocol. And now we can talk about how to implement it in a space efficient way with a streaming prover. And this mostly comes from facts about folding vectors in half. What we need to be able to do every time we do a reduction in the sum check protocol, we started with this input vector A, say, initially for the prover. And the new instance that we reduce to is this polynomial P of A evaluated at R1, or after 2 reductions evaluated at R1 and R2, and so on. And if you look at the coefficients of these, you end up folding the even and the odd coefficients together. So you've got, say, A0 plus this value R1 times A1. And basically the coefficients of this new polynomial, if we started off with coefficients from this vector A, the new coefficients that we end up with are this vector A prime, which is the even coefficients, plus the challenge times the odd ones. And then so on as we do more and more reductions all the way to the end of the protocol. So given streaming access to the original input value A, we've got to produce this A prime and all of the other values without using too much memory. And the way to do this, which comes from this prior work on streaming discrete logarithm-based arguments, is to get the first two entries of A and do the calculation for those to get the first entry of A prime. Get the next two entries of A and do the same thing to get the second entry of A prime, and then just so on, all the way to the end of the vector. And analyzing this, going over the whole vector A, which has length n, we needed to use a constant amount of memory to store two field elements at the same time. And one pass over this input vector A produced like one pass over this input vector A prime. And this kind of works again and again and again when we want to fold A prime into like A2 and all the way down to the end. So what this means is that after any number of reductions, the prover is able to produce, without using too much memory, a stream of like the polynomial coefficients that they need using O of n time and O of log n memory at most, if you add up all these contributions from folding at different levels. And this is done using just like one pass over the input.
So by the way, I have a question.
Yeah.
Can you hear me? I guess if you care about the IO cost, like I think streaming is not the best algorithm. There's a way, like if you use this unsafe bias layout, you tend to log n over log b, where b is the block size.
I didn't hear the name of the algorithm, sorry.
I guess you just want to have streaming. I guess maybe I'm confused about the goal. Is the goal just to have streaming, or you are trying to, because your motivation earlier sounded like you're trying to minimize the IO cost. But streaming is not necessarily the best for minimizing the IO cost. Like there are different goals. Like one is you just want streaming, but the other is like you want to minimize the IO cost. Minimizing the IO cost, you need to use external memory algorithm, and there's something called an unsafe bias layout that you do. I mean, I don't know if it applies here, but
okay.
you can get log n over log b.
Let's see. Actually, I'm not aware of that kind of algorithm. So yeah, maybe I'll ask you some questions about it later.
Okay, sounds good.
Yeah. Okay. So that's how to stream the input A and produce all these other inputs after various numbers of reductions for the sum check, without using too much memory. So in the end, the whole streaming algorithm for the scalar product protocol looks something like this. Starting off with streaming access to the inputs A and B. There's a way to incrementally compute the polynomials Qi that you need for the sum check after using this folding algorithm, using just a small amount of memory. And every time you want to produce one of these input vectors for the sum check, it takes you O of n time and O of log n memory with one pass. And to produce these sum check messages, that part I didn't explain, but that takes O of n time and a constant amount of memory and passes over the inputs. And so in total, over like a logarithmic number of rounds, you end up with n log n time, like a logarithmic memory consumption for the prover, and they've made a logarithmic number of passes over their inputs.
I guess in this case, is it that you have to really scan through everything? I guess if you really need to scan through everything, and maybe linear scan is the best. Like in that case, you'll get n over b. I guess there's a model, like you're talking about IO cost, there's a model to study these arguments called like the IO model, the external memory model.
Okay. Yeah.
But it sounds like you really need to scan through everything in this case. Like you have to catch every condition.
Yeah, you definitely need to access.
In this case, I guess maybe scanning is the best.
Okay, interesting. Yeah. Yeah, I'll have to think about that some more. Well, in any case, this is like our streaming algorithm for scalar products. So next, in order to get like a succinct discrete logarithm-based argument, which doesn't use too much memory, we've got to add in some commitments into this. So the commitment scheme we're going to use is the Patterson commitment scheme. And here we've got like a commitment key made of group elements, G0 up to Gn-1 from like a group of prime order. We've got a message vector A, which is the same as before. And the commitment is just this sum of products of messages times commitment key elements. Okay, so does anyone notice anything here about like the form of this commitment? Like, what does it look like?
Oh, no.
What was that, sorry?
It's an inner product.
Yeah, exactly. And we've already got a protocol for inner products. We've got a sum check protocol which works for inner products, a logarithmic amount of communication, like a good sound protocol, very efficient with a memory efficient prover. And we want to come up with a succinct argument for like an opening of this commitment. So we can just do exactly the same thing again. We can define like another polynomial, PA times PG. Brilliant, we're going to get a logarithmic communication protocol. This is fantastic. Maybe the only cause for concern here is that G is made up of group elements. So there are some questions like how exactly should you define a polynomial over a group of prime order? But this is not too difficult to do using scalar multiplication. You can imagine multiplying evaluation points in the field by coefficient elements in the group. So the protocol does generalize to this extent. The only real difference to take care of here is in soundness, because like normal soundness doesn't make sense anymore when proving knowledge of a message inside a Patterson commitment, because always for any choice of group elements, there are lots and lots of possible choices of message. So it doesn't make sense to ask for a normal soundness guarantee, because somehow the instance is always in the language. It makes sense to ask for a knowledge extraction guarantee, and replacing root counting with some like polynomial interpolation arguments. It's possible to come up with the knowledge extractor and show that any prover which passes the protocol should always know a suitable A, which is inside this commitment. And maybe surprisingly, this sum check based protocol is exactly the same as all these other discrete logarithm based arguments that I showed in that table before, maybe up to like some small changes of basis in the polynomials and so on. But the protocol you get here is more or less equivalent. In fact, there are only some small changes that you have to make from the original sum check. So the prover and verifier run a sum check protocol. And if you remember at the end of the sum check protocol, the verifier had to evaluate their polynomial at a random point. And at this time, the polynomial that we've picked is PA times PG. And PG is okay. The prover and the verifier both know G, so the verifier can evaluate the PG part, but only the prover knows the witness PA. So at the end of the protocol, to allow the verifier to perform their final check where they evaluate this polynomial, the prover has to send an evaluation of PA to the verifier. And then the verifier only evaluates this part of the polynomial for themselves in the end. So this is our argument for Patterson commitments. If we want to get an argument for scalar products, then it's very easy. We just do more and more of these in parallel. So pretty much the same as before. We can run another sum check protocol on these three products of polynomials in parallel. And then at the end of the protocol, the prover sends these evaluations of PA and PB to the verifier so they can perform their final check. And because of what we know about the properties of the sum check protocol and the fact that it's easy to fold vectors in half, everything about this scalar product protocol, all the memory efficient properties are just like instantly inherited from the memory efficient prover algorithm for like the normal scalar product protocol that we saw. So everything's quite nice and easy. So that was with discrete logarithm-based commitments. What if we want to go even further and do something that's not been done before? Construct like a memory-efficient protocol with some post-quantum commitments, or just in other cryptographic settings or something like that.
Is this a published work about the post-quantum?
No, it's not actually. I think so. Yeah, it's just it's a generalization that I think you can do. I don't see like what would go wrong with it, but no, it's not in any published work yet. No.
Thank you.
So are you going to explain the reduction from the circuit to scalar product and how to make that memory efficient? Or is it obvious, I mean, space efficient? Or is it obvious why that is space efficient?
So I would say, okay, I'm not going to explain it in the talk today. I think if you want to do it with like an inefficient verifier, I think it's relatively straightforward. I think to extend to the case where you have an efficient verifier is quite a bit more tricky, and for that, I'd probably refer you to this Gemini paper. But yeah, no, I'm not going to explain that today. I'm going to focus on different types of assumptions. I have a question in the chat. Do you just require D-log or knowledge of exponent? Just the discrete logarithm assumption, I guess, for what I've shown on the slide. So what I showed on the slide was like just a pure discrete logarithm based thing, and I've basically rederived this. Let me go to the next slide. Okay. Maybe I'll go back a bit. Actually, I need that table again. It's further back than I thought. Oh. Okay, yeah. So so essentially, I guess essentially what I've done here, I hope you can see my pen. I've kind of, by looking at the sum check protocol and its properties, I've kind of tried to like rederive or explain this work, which is just based on the discrete logarithm assumption. So you asked about the knowledge of exponent assumption. So this work on pairings does require the knowledge of exponent assumption there for those commitments. But yeah, this is the one that I've explained so far. So that's just all discrete logarithm based. Is KOE more efficient, would you say? Yeah, I think it is more efficient in practice. That's because the prover doesn't need to do quite so many calculations with the commitment keys in this knowledge of exponent setting, actually. So yeah, this one is faster and more practically efficient.
And also here, we don't actually care about zero knowledge, right?
No, that's right. Yeah, so this one, this argument here, this D-log argument here in this paper was actually zero knowledge. So these two were not zero knowledge, but I don't think this 2021 work was zero knowledge, but in any case, it's probably not too difficult to add the zero knowledge property to them. But no zero knowledge in today's talk.
The 21 work is zero knowledge.
Which one, sorry?
The 21.
Okay, yeah.
It is zero.
Okay, so yeah, so these two are zero knowledge. So then this one is not zero knowledge, but yeah, I don't think it's difficult to add it in. Okay, I'm just going to pause screen sharing so I can fast forward to the right slide again. Okay, found it. So how could we generalize this to different types of post-quantum commitments? So the first observation here is that, like, basically all commitment schemes, all homomorphic commitment schemes can be written in this scalar product form anyway. So if you have a message vector M, you can always express it as a sum of coefficients Mi multiplied by basis vectors Ei. And if you pull out these Mi's, then you have a scalar product of message entries and commitments to unit vectors. So we can just run like more scalar product protocols to check commitments in these different settings. If we want to do this kind of thing in an RSA or class group or group of unknown order setting, then the messages will be small integers and the key elements will be like group elements from a group of unknown order with some structure. And if we want to do this kind of thing based on lattices, then the messages will be small ring elements with like small coefficients, small norm or something in like a ring RQ of the type used in lattice cryptography. And then the keys will just be random elements from this ring RQ. So actually it's quite easy to generalize like once you've got to this point. Next slide. So in general, like the claim now, the only difference between this and like what we had before is that now we have some like norm constraints on the vectors A and B, like the message vectors inside the commitments. So again, we can just run the same kind of sum check protocol as before. Everything exactly the same. So one thing we need to add is like just a final check on the sizes of the evaluations that the prover sends to the verifier. We also need to make some changes to the challenge space used in the sum check protocol, because once we're working over the integers or over general rings, it's not always clear that you can do polynomial interpolation or bound the number of roots of a polynomial when you're not working over a field. So there need to be some changes there. And then this norm bound that's checked by the verifier at the end of the protocol is just kind of like the natural bound on the size of these polynomial evaluations that you would get just by working on the size of the elements of A and like the size of these elements in the challenge space. So kind of, instantly with this generalization, you can get like space efficient post-quantum arguments with streaming provers. Obviously with lattices, there are kind of additional technicalities and things related to relaxed soundness guarantees in the protocol, but yeah, really this is all handled by existing security arguments for like the non-space efficient provers. And so really working out the details for like a space efficient streaming argument is this is mostly about the prover computation. The security arguments have really already been done in these other works. So if we look at the kind of thing we've covered so far, basically explained like some key concepts which let you rederive at least up to a change of basis details on these discrete logarithm-based protocols, understand some of the lattice-based protocols, and like understand how to come up with streaming provers which are memory efficient and compute these protocols. So in the other cases where we work with like groups of unknown order or pairings, if you use these kind of techniques, you get related but not identical protocols, but with like similar efficiency properties to these published works. But I'm not going to talk about like the technicalities and like differences today. There's just not enough time. One of the problems with this lattice-based protocol that we've just come up with is the protocols that this one is based on have very poor concrete efficiency. So although this is maybe exciting in theory, it's probably not so good in practice. Like this Gemini protocol streamed to like extended to very, very large instances, but you wouldn't expect the same thing from this type of sum check based lattice protocol. So one question you could ask is, can actually practical lattice-based arguments be made more space efficient? And there are lots to choose from. I mean, there were already at least two at this year's crypto conference, and they're not succinct in theory. They have like linear or square root of n proof sizes, but they've got really good practical performance. So maybe they can be made space efficient. Maybe that's an exciting research direction. And another option is maybe we can just improve the theory of these lattice-based succinct arguments and actually make the space-efficient versions of them worth running in practice. I was going to talk a bit about this notion of sum check friendly commitments, but I think I'll skip over that in the interest of time. Is the bottleneck in PQC the lattice-based commitment efficiency? Question in the chat. It seems that there we do not have many techniques for them. Yeah, exactly. I think for like the succinct arguments that we know, it's relatively easy to come up with space efficient streaming stuff. It's not actually the streaming that's the big problem there. It's just that we need some good lattice based arguments and commitments to begin with to make space efficient, maybe. Or to design some completely new ones with good concrete efficiency in mind. So I think you're exactly right. Like basic techniques would be very helpful there. We need improvement in the basic techniques. Let me skip over these sum check friendly commitments. Okay, so the last thing I'm going to talk about today is possible generalizations to commitments with error correcting codes and hashes. So this is another way to build post-quantum succinct arguments. And here we'll be using code-based commitments. In this setting, we start off with a message and encode it using a linear error correcting code, and then hash all the entries of that error correcting code word up into a Merkle tree. To get a good code-based commitment scheme with good zero knowledge or succinct arguments associated with it, we need to use an error correcting code with good rate or good distance. Well, and good distance. And the Merkle tree part of this commitment scheme is streaming friendly. There are various protocols based on these code-based commitments using read Solomon codes. So there are deployed protocols like zero knowledge Starks and the Fry protocol, which are used in, I think, Stark decks like an exchange and in different practical applications. So they could be quite fast. And in theory, these are really exciting commitment schemes too. If you use linear time constructions of error correcting codes, these don't have like the same kind of folding protocol as before, but they've got their own sum check protocol, which can probably also make space efficient. And using codes like this is the only way to construct like really asymptotically optimal zero knowledge and succinct arguments where you really have like an O of n time prover and not like an O of lambda n time prover in the security parameters. So these types of arguments really have like the lowest possible computational overhead for the prover. So they're very exciting, but unfortunately, this error correcting code part of the commitment scheme is not streaming friendly. This is because if you change a later element of the message, then if you use an error correcting code with good distance, it should change lots and lots of different entries of the error correcting code. So just imagine you're receiving the elements like one by one as a stream, and you're trying to produce the elements of the the error creating code word as a stream, so you can feed them into some kind of space efficient Merkle tree algorithm. But then like a change in one of the later values in the message could possibly affect like earlier values in the error correcting code word, which you've already tried to hash into the Merkle tree. So you're already committed to those. And this is bad news because these succinct folding protocols for Reed-Solomon codes and this sum check for tensor codes are probably only easy to stream or like only have good space efficient properties if you're already working with like an encoding of the message and not starting with the original message. So this seems like bad news for these code-based commitments. I tried to think about like different ways to solve this problem. So my first thought was to use turbo-like codes, which have a kind of sliding window encoding algorithm. And in this case, if you take the original message and maybe you get several passes over permuted copies of the message, then to produce the code word, you kind of move over the message streams in like a sliding window algorithm, producing the entries of the code word one at a time. So this seems like it could be made like more memory efficient, but this is a bit of a stretch to the streaming model. It's not at all clear whether evaluating the entries of the message in this permuted out of order way is going to be at all efficient when you try and implement it. And also codes like this have really, really bad minimum distance guarantees. And there are actually some impossibility results saying that you can't have codes like this with really good minimum distance. So ultimately, these kinds of codes used in commitment schemes are just going to lead to very poor concrete efficiency, even if you do get like a memory efficient succinct argument at the end. Another way could be to encode the messages like in place in some kind of slow memory location before actually streaming any of the succinct arguments. So thinking of like an in-place FFT, maybe the prover has their message in their hard drive and they just encode it in place just once, which is really slow. But then after that, they can run loads of streaming proofs on it.
I have a question. I guess like FFT is known to have efficient external memory argument.
I'm sorry, I couldn't quite hear that.
I'm just saying that the butterfly network can have efficient external memory argument. I think you can't even compute it in a streaming setting to efficiently.
Okay. Yeah.
I can send you some pointers.
Yeah, please. Yeah, I'd really appreciate it. Yeah. So I guess finally, just like with the lattice-based arguments, there are some practical hash-based arguments which are not succinct, but which do have good space efficiency properties. So for example, there is an argument system, mac and cheese, which already supports streaming and has a very memory efficient prover algorithm, but this one has linear size proofs. So it doesn't meet our succinctness requirement, even though it can probably scale pretty well in terms of the prover algorithm. Or maybe we could actually just improve the theory behind these things and get some better constructions. Well, so I guess we'll end with a summary. So in today's talk, we've seen some of the techniques underlying like streaming provers that you could construct for succinct arguments based on different types of cryptographic assumptions. And by looking at this lattice case, I think it's pretty easy to see, based on all the prior work that's been done, that post-quantum space-efficient arguments are possible in theory. But since the constructions they're based on are not that concretely efficient, then they're probably going to be difficult to use in practice. But I think that this is like a big and exciting space to explore. And coming up with like more efficient succinct arguments that scale to really large instances. And yeah, I hope this talk has maybe sparked some new ideas. Certainly, I think I already came up with some new ideas while like trying to get this talk together. Thanks very much for your attention.
There's a question in chat.
Phi is code-based, but is efficient and deployable when compared to lattices. Unfortunately, it results in a large proof size. Do you think that code-based techniques can give new techniques insights for efficient lattice commitments, at least without hitting extreme friendliness or small proof size at first? That's a good question. So far, I actually don't know. I mean, I hope that the answer would be yes, but so far I don't have any ideas on how to do it. It seems like the lattice-based techniques really behave the same way, more or less, like other types of commitment schemes based on homomorphic cryptography, where the prover sends like homomorphically obtained like openings to commitments, so linear combinations of things. Whereas all the code-based techniques, on the whole, you open up different points. So yeah, I guess it seems to me like it's very hard to connect the two together. I haven't actually seen any particular construction of succinct argument that uses both types of techniques. So maybe it would be interesting to try and use them both at the same time. Yeah. Let's see. Okay. Any other questions?
Yeah, I think you can thank Jonathan. You can.
Yeah.
Or do you have-
I think there is no other question. Let's thank Jonathan again.
Oh, well, yeah, thanks very much for having me. And yeah, I'd really be interested to hear about these external memory algorithms as well. Thanks very much.
Thanks.